Welcome back everyone to another video, and we're back with the STAX journey, or STAX rabbit hole as it'll probably be known at some point soon. This is the STAX SRD7 audio transformer that comes out of the SRD7 transformer boxes, which I've gutted a couple of now, since we've completely surpassed them and I was trying to find other uses for them. We then moved on to the Lundahl LL1630PP, or push-pull. This is a vastly superior transformer with a similar footprint. You could probably fit these inside the SRD boxes, to be honest, but there's no give and take with these. These are vastly superior in every way, so it makes these completely redundant and you can just forget about them. Now, these transformers are almost perfect. They leave a few little things on the table around 20 hertz, 30 hertz, 40 hertz-ish in regards to how hard you can drive these transformers before they saturate. And that is about all that they leave on the table. They are almost perfect as is. And the beauty about these transformers is they do not need any external resistors or compensation to make them behave. They work as is, out of the box with a specific configuration set up on them. Right, so where do we go from here? Like I said, the Lundahl's are almost perfect. It would be good for probably 90% of users as is. It's very linear, it's very well behaved, and I just wanted to say also, which I don't think I've mentioned in other videos, a big thank you to Andrea, who wrote the original design for using these back in 2001. Yes, 2001. That's how old this concept is. And I'm incredibly grateful for what he did for the community. He, she, is it Andrea? I don't know. But it's been very beneficial for the STAX community, and I want to see if I can contribute a bit more to this. So we're going to see how far further we can go down this rabbit hole, and that brings in the Edcor, which is a CXPP 60-8-10K. This is a monster transformer. It's physically huge compared to the Lundahl. It's probably 4 to 6 times the weight, and the amount of iron this thing has, it should be vastly superior when it comes to lower frequencies and saturation. But I'm already seeing some red flags with this transformer, with its winding impedance that sort of is pointing towards it behaving more like an SRD transformer than a Lundahl out of the box, and I don't know how this is going to go down. So we will work on that in this video. We're also going to try something with the Lundahl that was never done by Andrea and see if we can take it even further and eliminate its one Achilles heel, I guess you would call it. So that's what's going to happen in this video. Let's get started by first comparing these transformers out of the box. So just sanity checking the primary windings on all the transformers before we get started. The original STAX was about 0.57, 56 ohms. The Edcor is 0.23, 24. Wow, that's really, really low. So this is the DC impedance. This is what the amplifier is going to see. And the Lundahl 1630, which is our benchmark, is about 6.4 ohms. Ooh, does not bode well for where we're heading. I can pretty much tell that this is not going to play ball like this did out of the box. These two are going to be very wild when we hook them directly up to an amplifier. So what I'm going to do is I'm going to plug it up to an amp I don't care about, and I'll show you what happens when you run these things without any resistors or anything like that. All right, so we're all set up with the STAX SRD original transformer. Going into 120 picofarad capacitor, this is simulating sort of a STAX ear speaker load as good as you can really do without actually connecting them up, which we are most definitely not doing. I'm going to only do this at 50 volts RMS. Normally I do it at 150 volts RMS, but at that voltage it's too dangerous for the amplifier this is connected to, and you'll see why in a second. So I am going to take this off a 1 kilohertz reference and we're going to sweep from 20 hertz to 20 kilohertz, and you will see what happens to the voltage. All right, so we did 3 cycles up to 20 kilohertz, and as you can see, the voltage just basically goes into a vertical climb almost. It cascades and it just runs away. If you did this 150 volts RMS, which I have done in the past before I learnt my lessons, you're going up into the 400 volt RMS range from your baseline, which shows that this transformer is not linear. It has big problems, and if you hook this up with nothing between it and the amplifier, you're going to have a really bad time with your frequency response, and probably blowing up the amplifier it's connected to. All right, so we've got the Edcor set up, same deal, 120 picofarad capacitor. We're going to sweep it again and see what happens. All right, so there you go. It is as bad or worse than the STAX transformer. I think it's worse because it was going out of range. Let me hook up the Lundahl and I'll show you what we're really looking at. Right, so Lundahl LL1630, same deal, exact same setup, 50 volts RMS baseline. Let's sweep it again. So that is what we want out of whatever audio transformer we are using. That this is the frequency response. We don't want the voltage to go up or down. I mean, it's going to move a little bit. It's not a perfect world, but you know, double the voltage is not a flat frequency response. In fact, it is downright dangerous for whatever you're connecting to it, and it will sound like absolute garbage. But this is so well behaved, and it is why it is a very special transformer, I think. Anyway, I'm going to go off screen and I'm going to do a little bit of work to the Edcor, and I will come back and let's see what we can do to it to make it well behaved. Okay, so this has been going on for a couple of days now. I've been going around in circles just trying to work out this diabolical transformer, like how I'm going to make this thing work. As it is not a happy transformer. Like it needs below 2 ohms on the primary side for it to not run away. I was able to find some happy places around 1.3 ohms, 1.5 ohms, but at the end of the day, that impedance is too low to drive from an amplifier. It is just asking for trouble. So I had to abandon just putting a resistor on the primary side, which is how the SRD transformers performed best. So like a 4.7 ohm resistor in series with the primary would keep these things happy. That is not going to happen with this transformer. So I had to start working on the output side, trying to balance this thing out. As it stands, I will not settle for anything less than 6 ohms on the primary impedance side, which is what the amplifier is going to see. So this is a 6.8 ohm resistor, and I've got an 8.2 ohm over here, and I've been going between those trying to find a happy balance. But with either of those on the input side, the transformer just falls. So you'll set 50 volts as the reference, and as the frequency climbs, it just falls off a cliff. So we have to go to this side and try to balance things out. So where did I end up? God, I'm trying to find what I'm looking for here. All right, 2K, 1.5K. All right, so this is where we were. 2K caused it to fall off, but not as sharply. It was starting to behave, okay? Then I went down the resistor ladder and I went to a 1.5. I was just sort of jumping in steps. As soon as I went to 1.5, the voltage started climbing after the reference voltage. So now I know, okay, we've crossed a tipping point. Something between 2K and 1.5K is where it is starting to reach equilibrium. So I went to a 1.8K on the output side, and just so everyone is clear, this is between the first set of taps and the outer taps. So the screen and the plate as it is labelled on this transformer, not between the centre tap. Or the centre tap, we might be able to do something with that, but these resistors are really struggling with the amount of power that we're testing, even at 50 volts. So this is just for testing. Then I need to go off and order high-powered resistors for all this crap to try and test this thing at much higher voltages and see what happens. But anyway, let me show you what happens with 1.8K on the secondary between the plate and the screen taps, and a 6.8 ohm resistor on the primary, which is about 7 ohms to the transformer now. All right, so we're all set up with the Edcor. Unfortunately, this voltage is going to start drifting quite a bit now because we have resistors on the input and output side. As everything heats up, the coefficients are going to change, and we're not going to have that like locked-in baseline that we used to have with other bare transformer setups, unfortunately. But let me sweep from 20 hertz to 20 kilohertz and show you what we've got now. So as you can see, it's sort of in the zone now. It basically has a bit of a climb, finds its equilibrium, and then it starts to taper off and fall. And that's telling me that we're sort of in the ballpark, we're within its envelope of operation, and there's probably something we can work with there and keep going. So I might order some big power resistors that can handle driving this thing up to higher voltages, and then we can see how bad it gets once the voltages climb, because then the error and the drift at those highs and lows are going to get even bigger, and we'll know what's going on there. But there is one sort of elephant in the room that I think needs mentioning, and that is that with all this resistor network stuff, we're creating a tuned frequency range for this transformer, and there's a lot of stuff going on with resistors on the output and the input side that we're not doing on the Lundahl, and it's creating like it's a little artificial, if I was to put it a certain way. Because let me show you what happens when I run this thing out to 30 kilohertz now. Right, so as you can see, beyond 20 kilohertz, it basically just falls off a cliff. Is that important to you? I don't know, but let me show you how far the Lundahl can go. So a sweep from 20 hertz to 30 kilohertz this time. And finally, just because we're here, let's take it out to 40 kilohertz. Anyway, what am I trying to say here? Well, I'm just trying to point out that bigger isn't always better. This transformer is going to have a lot more capacity at low frequencies, I think. We can't really test it till we get some big power resistors. But I just wanted to prove that this little guy can still do double the frequency range of that thing. Yes, you can't technically hear over 20 kilohertz, but there are crowds out there that claim that even though it's outside the audible range, it does create interactions between audible frequencies. And you don't want to just like close yourself into 20 hertz or 20 kilohertz and that's it. You want as much bandwidth as you can have without just chopping it off like a cliff. Yeah, I just thought that was worth explaining, that this thing is, as it is, even with all the resistors and everything, it appears that it's going to be a very limited scope of operation, and we maybe won't be able to get it to go like this massive bandwidth range. If something can change with some big power resistors and we can do more testing, we're going to have to come back to this thing. But I want to show you one other thing with this Lundahl that I am pondering, but it may not be feasible, or maybe it will be, I don't know. Okay, so this is my alternative setup that I'm currently playing with. So this is two Lundahl 1630s in sort of parallel on the primary side and series on the secondary side. What this sort of achieves is it doubles the saturation point essentially, because the transformers are teamed up now and working together. And so basically on the primary side, all the windings are in parallel. There is essentially 4 coils on the primary side, so they're all paralleled, which gives it a total of about 3.6 ohms. And yes, I know I said 6 ohms was the minimum, but just for this setup, this is what we work with because this is the coil impedance and we can either have them in series or parallel. That's our only choice. We can't do anything other than that. On the output side, we have everything in series. So the new center tap is sort of in the middle here. And we have doubled the taps end to end by putting it in series, which gives us double the voltage swing, essentially. We're not playing around anymore. We're going up into the big boy voltage ranges. We're not doing 50 volts anymore. So let's do a 20 hertz to 20 kilohertz voltage sweep again and see what happens at 150 volts baseline. Everything looking good at 20 hertz to 20 kilohertz, still hanging in there. So let's push it out to 30 kilohertz and see how much more it drifts. Yeah, so overall, even up to 30 kilohertz, these are still hanging in there. It is deviating a little bit more, but it's going to grow the more we go up in voltage. So we just have to keep that in mind. We also need to keep in mind this is with one amplifier. I have another amplifier I intend to use, which is going to give us different readings, but I'm not going to risk more expensive, more capable amplifiers until this setup proves itself on low-end amplifiers, because I can't risk blowing up some of my prized possessions just screwing around with this stuff. So let me just show you what the saturation is now with 2 of these versus 1 of them. So this should give us the best view we can get. We're at 20 hertz, sort of 150 volts as per usual. We're going to start cranking this up and see when it saturates. Now this would normally happen at about 270 to 80 volts RMS. This is in RMS. So we're going to see what 2 transformers can do in this situation. And well, there you go. We're already past it. It's still holding. Climbing. Wow, okay, we're really getting up there now. 500 volts. And I think I can start to see a notch happening. Yep, there it goes. So you see that notch in the middle there? That is the core's saturating. So we're looking at about 500, maybe 540. I would say more like 511 volts. And if you keep going, it just really notches over. So you can see how bad, that's what core saturation looks like at these lower frequencies. But we're doing 511 volts RMS here, and I would say that is perfectly clean. I think you could even go to 540 technically, and you probably wouldn't even notice that, but I can see a little bit of a notch in the sine wave there. So yeah, 2 transformers does essentially double the saturation point. Right, so we're going to close this video out here and just see what else I can come up with. I need to get my thoughts together and ponder these 2 transformers and what else is out there, where we go from here. The 1630s, I think overall are giving me more confidence. I just feel better about them. but I'm not sure if this configuration is creating other problems around distortion or phase or whatnot. I am concerned about the primary windings in regards to that they're dropping down to about 3.6 ohms and what that is potentially doing for any amplifier that is driving this setup, and if there's any dangers there, because I would prefer them to stay up around the 6 ohm minimum range, but that's not feasible with these as is without adding resistors and other stuff into the mix, which we're trying to avoid. The Edcor is just up in the air at the moment. I'm not convinced this thing is going to work out for me. The bandwidth is just like very limited, and it just doesn't give me the warm fuzzies like the 1630 did with it just working out of the box. If anyone who has transformer experience wants to chime in and give some feedback, comments, please let me know. I need to do more research on this. I'll order some big power resistors either way, but it feels like we're sort of boxed in with this transformer in where we can go with it. Who knows? We'll see what happens in the next video, and maybe some other transformers will come along the line that can enter this battle royale for the best STAX transformer that is out there. Until the next video, I will see you in the next video.